Hello guys, you welcome to my channel. Today we want to talk about a simple harmonic motion. When you talk about a simple harmonic motion, we talk about a periodic motion. An example of a periodic motion is a system of spring and mass. That is the mass spring system and the simple pendulum. But in this class, I want to talk about the mass spring system. Now, let's see what we call a simple harmonic motion. If I have a string like this, so I have a mass attached on the string, and the equilibrium position of the string is here. Now, let's pay maximum attention so that we understand what we call a periodic motion. Now, when I apply force to this body, the applied force is taking the body downward. Before releasing this mass, there is a certain force known as the restoring force that wants to take this body back to the equilibrium position. You know, the applied force is taking the body away from the equilibrium position. The restoring force is ready to take the body back to equilibrium position. Now, by the time I release this mass, the restoring force is going to take the body back to equilibrium position, and once it gets to equilibrium position, the restoring force becomes zero. But because this body has a mass and it also has velocity, momentum of this body is going to push it backward. When it pushes it beyond the equilibrium position, the restoring force is going to build up again to push the body downward. So when the restoring force pushes it downward, it's also going to build it upward again. So when it pushes it upward again, it's still going to push it backward. The to and fro movement is what we call the periodic motion. Now, let us understand something about this body. Now, if I apply this force on this particular body, the body is pointing in a downward direction, which simply means that the displacement vector is facing downward, and the restoring force is facing upward. Automatically, the restoring force is moving in opposite direction to the displacement vector. Hence, we have that F, which is the restoring force, from Hooke's law to be negative kx. The negative is to tell you that the restoring force is moving in opposite direction to the displacement vector. Now, let's get something clear here. What is the significance of x? X is said to be the displacement from the equilibrium position to the current position. In other words, we call this one extension. Now, what is K? K is force constant. Force constant simply means a unit force that will cause a unit extension on the string. Now, let's take for instance that the K, which is the force constant, is 20 Newton per meter. What this simply means is that for us to stretch this particular string or to compress it by 1 meter, we need a force of 20 Newton. For you to compress it by 1 meter or you extend it by 1 meter, you need a force of 20 Newton. If you are to double the extension or the compression, you need a force of 40 Newton. That is, you also have to double this. Now, if I now have that the string is about 4,000 Newton per meter, this is a very high stiffness. That is, if I will compress the string whose force constant is 4,000 Newton per meter, I need a force of 4,000 Newton to compress it by 1 meter or to extend it by 1 meter. Hence, you will see that this is a stiff string and this one is a loose string. Okay, class, now let us now discuss something else regarding this particular motion, which we regard as mass string system. So if I have this, let's say I have this, and this is mass M, and I have this is also mass M, and I have this, and this is mass M. Now let's say this is the equilibrium position. Let me use another color for better understanding. If this is the equilibrium position of the string, when I apply force Fa to this body, the force is pointing downward, and a force is ready to take the body back to the equilibrium position. That force is the restoring force. Now watch, as at this time that I'm yet to release this body, the total force on this system, that is the net force on the system, is 0. Why? Because the applied force is equivalent to the restoring force at this moment. Now, by the time I release the body, the applied force said to disappear, and I'm going to have my restoring force only to take the body back to equilibrium position. So, when the restoring force gets back to the equilibrium position, it becomes 0. Why? Because the displacement x is equals to 0 here. And you know, the restoring force is kx. 0 times k will give us 0. That's why this is 0 here. Now watch. By the time this body becomes 0, that is, before I release this mass, the whole of the force in it is equals to 0. When I release the mass, the applied force will disappear. The total net force on this system is going to be the restoring force. When the restoring force gets to the center, that is the equilibrium position, it becomes what? 0. Then momentum is going to take the body, because the force is already 0. Momentum is going to take the body from this equilibrium position to compress. When the body compresses, this force is set to build up again to push the body towards the equilibrium position again. So, if this should be the case, at this point, we have that our displacement is maximum. When displacement is maximum, we call it what? Amplitude. Now, you will agree with me that initially, when we have not released this body, the velocity on this body is 0. Are we together? If the velocity is 0 and we have our displacement to be maximum, our acceleration would also be maximum. Are we together? If we are together, let us move down to the second body, whereby the body is at equilibrium position. The second body is at equilibrium, right? This one extends, that is, we stretch this one, and this one is at equilibrium. At the equilibrium position, remember, the restoring force has provided what? A velocity. Now, the velocity at this center is set to the maximum. If the velocity is maximum at this center, then we are going to have our displacement to be 0. If displacement is 0, acceleration is also 0 at this equilibrium position. Remember, our restoring force is also going to be 0 at the equilibrium position. Now, when the body compresses, by the time the body compresses, remember, it is the momentum that caused the body to compress. When the body compresses completely, the restoring force is set to build up again to push the body downward. Hence, our x at this place is also maximum. And our velocity has become what? 0. Hence, we also have acceleration here to be maximum. So, if this should be the case, we can then talk about the energy of this system. Remember, your kinetic energy is a function of velocity. So we have kinetic energy to equal 1 over 2 mv squared. Now, if v is equals to 0 at this point, kinetic energy is said to be 0. And if x is maximum, we have our potential energy at this point to be 1 over 2 kx squared. So it means that potential energy is present here while kinetic energy is 0. Now at the equilibrium position, the displacement is equal to 0, but we have our velocity to be maximum. Hence, potential energy is 0, and we have our kinetic energy to be maximum at the equilibrium position. And here, when the body fully compressed, potential energy is maximum, kinetic energy is 0. So with this, we can talk about the total energy of the system. And what will be the total energy of the system? The total energy of the system is going to be the summation of the kinetic energy and the potential energy, which is then going to equal to mechanical energy. Remember, when x is maximum is equals to the displacement. By the time you release the mass, if this is the point at which you release the mass, this body will never get to this point again. If the law of conservation of energy is what? Is conserved in this place. That is, if energy is conserved there, and the law of mechanical energy holds in this particular place, this body will not get to this point again. Hence, our mechanical energy is a function of amplitude. So we have that mechanical energy, which is equal to potential energy plus the kinetic energy. So this will be 1 over 2 Ka squared. Potential energy is 1 over 2 Kx squared plus 1 over 2 mv squared. Let's call this equation 1. Now, let us now understand what happened at every instance, because if friction is not what involved, the mechanical energy of the system tends to be constant. So, at this point, when x is maximum, the velocity is equal to 0. Hence, when x is maximum, the total energy of the system will make mechanical energy to equal potential energy, because by the time you put 0 here, this kinetic energy becomes 0. So when x is maximum, mechanical energy is equal to potential energy. Now, when v is maximum, x becomes what? 0. Hence, mechanical energy is equal to kinetic energy. So, let us note that and call this equation star. Now, you might now have interest to know the maximum velocity of this particular system. How can we get the maximum velocity? Remember, when the velocity is maximum, the displacement is equal to 0, which means the body is at equilibrium position. Hence, I'm going to have this to be 1 over 2 Ka squared to equal 1 over 2 mv squared. So, if I multiply both sides by 2, 2 times 1 over 2 is going to give us 1. 1 times this will give us Ka squared. And this will also become mv squared. Hence, I have that v squared is k over ma squared. So if I take the square root of both sides, v is equal to the square root of Ka squared over m. And this is equal to a square root of k over m. Hence, our maximum velocity, the velocity max, is equal to a root k over m. Let's call this equation 2. So, if you are looking for the maximum velocity of this system, the maximum velocity is amplitude times the square root of the spring constant divided by the mass. Now, we might not be interested to know the maximum velocity, but we want to know the velocity at every instance. How can we get that? Now, let's see. That is, the velocity at this time around is not maximum. Now, let's go back to the initial equation, that is equation 1, where we have 1 over 2 Ka square to equal 1 over 2 Kx square plus 1 over 2 mv square. At this point, take this one to the other side. We have 1 over 2 Ka square minus 1 over 2 Kx square equal 1 over 2 mv square. Guys, if you multiply through by 2, we are going to have that Ka square minus Kx square equal mv square. Now, if you look at this, k is common. If I factorize it out, I have k into a square minus x square equal mv square. If this should be the case, divide both sides by m. V square equal k over m into a square minus x square. Now, let us try to write this equation in form of what? As a function of the maximum velocity. So, if we are going to do that, let's factorize out a square. If I factorize out a square here, I will have k over m into a square, 1 minus x square over a square. Mathematically, if I open this bracket back with a square times 1, I have a square times x square over a square. This a square will cancel this, so I will have this back, so we've not done anything wrong mathematically. So, if I take the square root of both sides, v will become the square root of k over m a square into 1 minus x square over a square. So you can split what? You can split this square root. If I'm going to split the square root, I'm going to have something like this. So I'm going to have that v is equal to the square root of k over m times a, then the square root of 1 minus x square over a square. And if you look at this, this is the same thing as the maximum velocity. Hence, the velocity at every instance is maximum velocity times the square root of 1 minus x square over a square. And this would be our third equation. Okay, what about the acceleration of the body? We have understand how to calculate for the maximum what? Maximum velocity and velocity at every instance. Now, how can we then calculate for the acceleration? To calculate for the acceleration, we recall that the restoring force is equal to kx. Okay, let me make this another color so that we can see it clearly. If I have that the restoring force F is equal to kx, let's forget about the negative sign now. So we are considering this. Remember, the negative sign is just to tell you that it's moving in opposite direction to the displacement vector. It's not that maybe it's affecting the magnitude, but to tell you the direction in which it's facing. Now, if F is equals to kx, we also have from the second law of motion that F is equal to ma. So this and this would equal to each other. I will then have that ma is kx. Hence, a is said to be kx over m. And this would be our equation 4. This is acceleration at every instance. So, if you want to calculate for the acceleration of the body at every instance, we have this. But what of maximum acceleration? Acceleration is said to be maximum when the displacement is maximum. And when the displacement is maximum is equal to the amplitude. Hence, if I put this in place of this, maximum acceleration is Ka over m. And this is equation 5. Now, you will all agree with me that we can calculate for the velocity of the body, the maximum velocity, acceleration at every instance, and maximum acceleration. Okay, if that should be the case, let's talk about the period and frequency of this body. At this point in time, I would like to consider the string to move in horizontal for better understanding of this. Let's say we have an horizontal wall and the string is like this. Are we together? Yes. Now, if this is the equilibrium position of this body, by the time this body moves from the equilibrium position down to this place, that is, okay, let's take for instance now that you've released the body will move from this point back to the equilibrium position. Let's say that is x. From here to this place is going to move again, that is x. And from here is going to move down to this place, that is another x. From here is going to move down to this place, we have another x. Hence, the total distance covered by this body, distance, is going to be 4x. Remember, a distance is a scalar quantity, so direction is not considered here. That's why this is equal to 4x. Forget about the direction now. Now, if x is maximum, is equal to the amplitude, right? Hence, distance is equals to 4a. Now, when the body moves from here down to this place, that is what? Half circle. And when the body moves from here down to this place, that is another half circle. Half circle plus half circle, that gives us a complete circle. So, one circle is equivalent to one oscillation. So, when I say one oscillation, that is the to and fro. When the body moves like this, to and fro, that is when the body has one oscillation. Now, the body has what? One oscillation. Now, what is period and what is frequency? Be right back. Yeah, I'm back. I'm very sorry, it's my camera that is doing that. So, now let's quickly look at it continuously. Now, one circle is when this body moves to and fro like this. It has complete one oscillation. And what is period? A period is the time taken to complete one circle. A period is the time taken to complete one circle. So, if the time taken to complete one circle is period, hence the period is going to be the time taken divided by the number of cycle. So let me put this as hash. So the time taken divided by the number of cycle will give you period. Let's take for instance that you have what? 40 seconds for you to count 4 oscillation. So if you count 4 cycles for 40 seconds, what is going to be the period? The period is going to be 10 seconds. It means it takes 10 seconds to count one cycle. Now what is now going to be the frequency? Frequency is the number of cycles per seconds. The number of oscillation per seconds is frequency. Hence, if I have frequency is going to be the number of cycles divided by the time taken. Hence, if I have this particular body now, if the number of cycles is 4, and the time taken to count 4 is 40, our frequency is going to be 1/10. Hence, this is 0.1 hertz. It means for every seconds you complete 0.1 cycle. I believe we understand that. Now, this is just this. It shows that period is 1/frequency and frequency is 1/period. So let's call this equation 6. Okay, since we have been talking about acceleration and velocity in terms of what? Spring constant and the mass. Now let us also talk about what? Period and frequency in terms of what? The spring constant and also the mass of the body. Pay attention, class. Okay, if you are with me, I would like us to go into that. Let's consider a body that is performing a circular motion like my wristwatch. If you look at my wristwatch, if it starts to move from here, let me say this is point A, and the wristwatch move to another point B here, and it moves from another point B down to another point C. If you look at this, let's say this is the diameter. If you look at it now, it will look like this body is moving towards the negative axis of X, because if this is the center of this circle, here is going to be positive X and here is going to be negative X. So if you look at the circle horizontally, it looks like the body is moving in the X plane. Abi? Yes. This will be the maximum displacement of the body, which we call the amplitude. Okay? If this is the amplitude, here is our X and here is angle theta. By the time this body moves to this place, it's going to move down to another point D here. And by that time, you will see that the body has started moving from the negative axis going towards the positive axis. By the time it gets to this place also, it returns back to A. You see? So it shows that the body is moving like this and like this. So this motion will continue back and forth, and that's why we said the second hand of this wristwatch is also a simple harmonic motion. Now, if this body is performing a simple harmonic motion like we just explained now, we are going to have that the velocity is displacement divided by the time. And the time that will take this body to move from here and come back to this place is known as the period of oscillation. Now, the total distance covered is the circumference of this circle. And the circumference of a circle is 2 pi r, or this. The circumference of a circle is 2 pi r. So the velocity will be 2 pi r divided by t. Abi? Yes. Yes. Okay? If that should be the case, our r is radius. Looking at this diagram, our radius is our amplitude. Hence, V is 2 pi A over T. So if I make T the surface of the formula, I will have that T is 2 pi A all over V. So let's call this equation equation 7. Now, I know that velocity is expressed in terms of amplitude. So let us go back to the formula for maximum velocity. We have that our maximum velocity, if you can recall vividly, our maximum velocity is A times the square root of K over M. Can you recall? Okay, if this should be the case, let's make what? A the subject of the formula. If I do so, I will have that V max is the square root of M over K, and that equals to what? A. That is, I multiply both sides by the reciprocal of this, which is M over K. You know, this and this would cancel, and this would cancel. Why this will multiply this? Okay? I believe you are getting what we call a simple harmonic motion right now. Okay? If that should be the case, let's quickly slot this into this equation. So I have that the period is going to be 2 pi divided by V times A is now going to be V the square root of M over K. V and V would cancel. So the period is going to be 2 pi the square root of M over K. So let's call this equation 8. Okay, guys, I'm happy teaching physics, and I know you're happy learning physics as well. If that should be the case, let's move on from here. But before I go on, I would like to explain how this will affect the period. When the mass of a substance is very high, the period is said to be high as well. That is, if the K is small, the period is said to be high, and if K is high, the period is said to be small. Okay, now we have that frequency is 1 over period. So frequency in terms of this, we are going to have that F is 1 over 2 pi, the square root of K over N. So this will be equation 9. So we have expressed what? Frequency in terms of the spring constant and the mass, likewise the period in terms of the spring constant and the mass. Now, let's see, what again do we need to understand about the simple harmonic motion of a spring? Now, let's look at something. You're welcome back. Now, if you look at this, if I have that the string is oscillating within this point and this point. So if I plot the graph of the displacement, the maximum displacement of this motion that we're talking about since is the amplitude. And the minimum displacement will also be negative amplitude. In other words, the value of x range between negative a and positive a, inclusive. That is, x can equal to a or less than a, and also it can equal to negative a or greater than negative a, but it can't go beyond a. Now, if I have my time at this horizontal level, if I plot the graph of a against t, that is the displacement against time, I'm going to have a cosine graph. I'm going to have a cosine graph if I start from there. But if I start from the equilibrium position, that is the middle, I'm going to have a sinusoidal graph. And I can also decide to start from this point here, which is going to give me a negative A negative cos function. So I will have this. Are we together? Okay, don't let us go much into this now. Just trying to show you the way we can have this particular graph. Now, how can we make use of this graph to find, should in case this graph is given to you and you are asked to look for maximum velocity, you are also asked to look for the maximum acceleration. How can you go about that? Now let's see. I'll quickly recall us back to this circle. Remember, this is the circle we have initially when we are talking about the period and frequency. If this is our maximum displacement and here is x, so this point here is angle theta. If I trace this down, this will be vertical axis. Now, from the trigonometry ratio, I will have that the cosine of theta is x over a. If I cross multiply, I have a cos theta to equal to x. Let's say this is our equation 10. If this is our equation 10, x is equal to a cos theta. Now, recall that the angular momentum is given as the angular displacement per time. That is the angular displacement per second. So, theta is going to be omega t. And our linear velocity is going to be linear displacement per second. So, our displacement is going to be what? Vt. Yes, our displacement is going to be what? Vt. While our angular displacement is omega t. Now, if I replace this omega t, if I replace this theta with omega t, I'm going to have that x equal what? A cos theta. Instead of that, I'll have x equal what? A cos omega t. But before then, omega is 2 pi f. Okay? X is now A cos 2 pi ft. Because theta is omega t, omega is 2 pi f. If you put it here, you have what? 2 pi ft. So use this to replace what? Theta. No qualms. Okay, we are going to need the knowledge of calculus here, because by the time you take the derivative of displacement in respect to what? Time, your result is going to be velocity. Why? Velocity is equals to displacement over time. So the x dt of this function, this is going to be a chain rule. I'm going to differentiate 2 pi ft first. When you differentiate 2 pi ft, your result is going to be 2 pi f. So I have a2, it's okay, let me just write down. Let this 2 pi f, let me bring it here. Are we together? Now I'm now going to differentiate cos of this now. The derivative of a cos is negative sine. Are we together? Hence, v, which is a function of time, is equal to a negative a 2 pi f sine 2 pi ft. Do we get this? But we are not done there yet. Let's quickly come back here and see what will happen. Now, remember that our frequency is given as what? Let's see. Our v of t, remember a is, we have, let's say 2 pi f negative 2 pi fe sine 2 pi ft, if this is what we have. Now, what is our f? Our f is given as 1 over 2 pi the square root of the square root of k over m. That's our f, isn't it? So let's slot this into this. We have that v of t is negative 2 pi times 1 over 2 pi the square root of k over m a sine 2 pi ft. This and this would cancel. If this and this should cancel, v of t is equal to negative the square root of k over m times a sine of 2 pi ft. Now, remember that the square root of k over m times a is the same thing as maximum velocity. Do you agree with me? If yes, the velocity as a function of time is negative v max sine 2 pi ft, equation 11. So we can now look for acceleration now. Remember, acceleration is the derivative of velocity with respect to time. So we have dv dt to equal, now at this junction now, I have to differentiate this one again. If I differentiate this, I will still have 2 pi f, right? So, okay, don't let us start from here. We are going to run into trouble if we start from here. Let's just, let's start from this point here. Are we together? Okay? If I start from this point here, I will have that this now is going to be 2 pi when I 2 pi f when I differentiate it. So use this to multiply this. I'm going to have negative 2 pi square f square times a, and this is going to be cos of 2 pi ft. That's what the derivative will give me. So you can lay your hand more on calculus. Okay, now let's see what will happen there. If this is f square and this is 2 pi, 2 pi square. So this is supposed to be 4 pi square. Sorry, because these two will multiply these two also. Yes, yes. Sorry for the mistake. Now, if I square this equation there, my result will be 1 over 4 pi k over m. Is that not? So if I slot this into this place, I will then have that negative pi squared times f squared is 1 over 4 pi k over m times a cos 2 pi ft. Mind you, you don't need to change the value of f here. Okay? This now, this is going to be square also, sorry. So this and this would cancel. So I will have that a is equal to negative k over ma cos of 2 pi ft. Okay? If you remember, this is going to be our maximum acceleration. Hence, a is negative what? A max cos of 2 pi ft, equation 12. I believe you understand this. Is it not difficult? No. Don't perceive it as difficult. It's very, very what? Easy to achieve. You can go back to the video again if you are getting anything wrong again. Okay? This will be the end of the class today. By His grace, in our next class, where we are going to be talking about what? The simple harmonic motion of a pendulum. But before then, we have to look at problem on this particular one that we just did now. And then I will be talking about damped oscillation. And I'm going to be talking about what? Resonance and forced frequency. At this junction, thanks for watching and thanks for liking physics. Good day.